The purpose of this video tutorial is to show how we can model and analyze frame structures in Adapt Builder. In this example, we'll be using Builder 2016, and we're going to, in essence, have only columns and beam elements. We're not going to have any slabs, so we're not relying on the production of shell elements for the purposes of solving the problem in this example. To begin, in the splash screen of Builder, we're going to ensure that we have Edge turned on and also Floor Pro, and we're going to use American System of Units for this example, and we'll just do an RC frame, and we'll select OK, and we'll go ahead. In the modeling interface, we're mainly going to be using the Build toolbar, and I'm also going to use the Grid toolbar, so we'll go ahead and turn on the grids, and then I'll make a grid, let's just say of 10 feet here. There are other ways of importing frames or structures into the program, which are covered in supplemental tutorial videos located on our YouTube channel. So check those out when you have a moment to quickly and rapidly import structures into Builder. In this example, we'll do a 5-story frame. So I want to use the Story Manager toolbar, and under the level assignment, we can also get here from the Build options, construction aids, level assignment, and here we're just going to add 2 more floors. So we'll go ahead and add 2 additional levels. I'll make this consistent in how these are named, so we'll call this plane 3. The current plane I'll rename to plane 2, and then bottom I'll just say is the base. And we'll leave the heights here to 10 feet. We'll say close. We're going to open the Build toolbar, so we'll go to User Interface and we'll select Build toolbar. That's going to dock at the right hand side. I'll just bring that in here to this working space. And you can also use the Build structural components from the option Build structural components and add slabs, columns, walls, etc. So one of the main and most important factors that needs to be used when you're modeling a frame is that columns and beams need to align at their centroids. So when we use a slab, we can actually connect different components through the shell elements, through node shifting and offsetting. But when we have a pure skeletal frame, we want to make sure that we're connecting everything together. So let's go ahead and turn back on our grid. This again is 10 feet by 10 feet. The working plane that we're looking at currently is level 2. So this is the first elevated floor. And we'll just do a very quick example, and then we'll build on this example. So I'm just going to go ahead and add a column. The column we'll say is 20 by 20, and we'll just assume the default material assignments, concrete 1. We can go here and just add a 40-foot span with columns. So I'll add a beam along that span. If we add a beam, we can go from this point over to this point. Remember, we're connecting them at their centroids, and I'll show you how to check to make sure that they're connected at their centroids in a moment. For this beam, we're going to say this beam is going to be 18 inches, and we'll say it's 24 inches deep. So we have our beam now, and currently we have no loads on this. If I go to the rendered view, you can see this is just one simple frame with 2 columns at the ends. We're working in single level mode, so the default boundary conditions in single level mode are set in criteria, and we can see that for the default, if we go to analysis and design options, this is set as a fixed roller. So the user can change this under single level to whatever other boundary conditions you want. Let's go ahead and save the model. And after we save the model, we're going to run the analysis. We don't have any load yet. We're only considering self-weight. But if we go to FEM, and naturally if you've used Builder before, one of the things you're always used to doing is meshing the slab. In this case, we can skip the automatic mesh. This is actually used to mesh the slabs and walls. This is the automatic mesher that subdivides slabs into shells. So we're just going to skip down to analyze structure, and that will allow us to select the the same analysis options that we would have in a regular slab model. If I select OK, the program is going to ask me what the discretization is for the frame meshing. So we'll say we want to split this beam into 4-foot chunks. We'll say OK. The program analyzes the frame, and we get similar result capabilities as we would with any other model. So for this particular example, if I first look at, for example, the bending moments, notice that we don't have any support lines, no design strips yet. We only have a beam and 2 columns. So if I go up to beam and I look at the axial force, for example, or let's say the bending, this is showing us our bending moment relative to the analysis. And for this bending moment, let's go ahead and turn on the support line results toolbar. You can see that if I values here, and I'll also turn off the projected shape, this bending moment is relative to the beam frame elements. The beam frame elements can be displayed from select set view items, finite element, frame element. And again, this was subdivided into 4-foot chunks, so there are 10 frame elements along the length of the beam. There's 2 along the height of the column. And if we go to column, for example, I go over here to column, and here in the column I can look at axial forces for columns, I can look at the shears, moments, and so on for this particular frame. Like any other model, we can add loads to the frame so long as the loads are along the longitudinal center line of the beam element. So we're going to go ahead and turn off these results. We'll just restore this back to the model that we had earlier. I'll turn off the column and wall actions. Let's go up to column and turn column off. And I'm going to go back to a plan view. And from loading, I'll add load, line load. We'll use the snap endpoint tool, and I'll just add a line load from one column to the next. And let's go back. So we add this line load here. And we'll change that to a live load. This might be, let's say, 3 kips per foot. And again, we can reanalyze once we've added load to a particular frame. We have load combinations that are defined under loading, load combinations. Here we can define our combos per the load cases that are created. And again, we go back, analyze a structure. It will ask us to remesh. We'll just keep the 4-foot mesh. And again, we have results for the system. So for example, if I look at the strength dead and live moments for the beam, we have a moment here at this beam frame element roughly 672 kip feet. So these are just raw frame results. We need to have some sort of way to design for those moments. And in order to design for the moments, we need to introduce support lines along this frame. So if I go and, for example, select the option for strips, create a support line, we'll just create a support line along that beam line. And just as we would do with the slab model, I'll go ahead and generate the design cuts. We generate the design cuts. After we've run the analysis, we can design the design sections. So now we design those sections, and let's go back to a 3D view. If you recall, the beam element moment was 672 kip feet. Now I'm using design sections, which utilizes integration of nodes, either frame or shell nodes. And for this case, we have a moment along this strip of 672. So this should be identical to the beam moment. Now there is a case that the results don't exactly match, and that's simply because the discretization of the frame elements and the increment of distance between frame elements may not align perfectly with the increment of design cuts. So in other words, you're interpolating between two nodes along the beam frame element, but they're close. So these particular values for design sections now, not beam moments, but design section moments can be designed for. So if I go and take this in an extra step, if I go to FEM, generate rebar, and we'll just look at the strength dead and live case, you can see the program has designed this beam for reinforcing. There's 11 number 8 bars in this beam, and that's shown here. There's also some top reinforcement as well. This is just an RC beam. If you double click on the design cut, for example at this moment of 672, and go to design sections, now we can see the amount of reinforcing that's needed in the beam. There's 7.9 square inches of steel needed for strength dead and live for this particular section. And if you go to details, this is actually telling us case 3 is controlling the design. So what this means is that the section capacity was not sufficient for base reinforcement. There was no base reinforcement. So the program is actually having to add both tension steel and compression steel to meet the ductility required to keep this a tension controlled section. That's what this case is indicating. Alright, so now we're going to kind of build this out a little bit further and do a multi-story this example. So let's go ahead and I'll go back to my default display. I'll turn my grids back on. And what I can do in this case, I'm going to copy this frame upward, and I'm turning the grids on just as a reference to see kind of what distances we're copying it. We're just going to do 40 foot by 40 foot bays, and I'll copy this using modify, copy, move. We're going to copy this using all transformations in the XY plane, and we're going to copy this 40 feet, and we'll do 3 bays, 3 copies, let's say. We'll copy it that way. And then we're going to copy this over. Now for this copy I'm actually going to use a different tool for modify, copy, move, and we're going to graphically translate the what is selected. So I'll take this and I'll move it 1, 2, 3, 4, and we'll say copy, and then we'll go ahead and fill. I'll do the same with this beam. We'll go back to modify, copy, move, and I'll move that beam from there to there. And then I'll replicate that beam down negative 40 feet. It's in the negative Y direction, and we'll do 3 times. Okay, and then we'll take this beam element. I'll create 1 row of beams there, and we're going to copy this over again. Here we'll copy this over 40 feet 3 times. Okay, and so now we have our frame at the lower level, and everything here is aligned at the centroids of the columns. If I look at this frame, this is basically what we have currently. We'll go ahead and take this now, and we're going to copy this vertically as well. So I'll use the Story Manager toolbar. I could also go to Modify, Copy, Move Vertical. On the Story Manager toolbar, this tool looks like, let me grab those again, looks like this. This is Copy, Move Vertical. We're going to copy up 4 times. Now I'm in single level mode, so I'm only showing the active plane, and right now the active plane is plane 2. If I go to multi-story mode, I'm now looking at the entire structure, and the entire structure looks something like this. So once I've created this multi-story structure, I want to make sure I'm analyzing this in multi-story mode or full structure mode. We can still analyze in single level and navigate up and analyze a single frame, or we can analyze a multi-story frame. From criteria, analysis and design options, we have multi-level as well as single level. So multi-level indicates what the conditions are for supports, when you run the model using multi-story mode. And in this case, the default is fixed. Also, by default, all of the columns and beams are not released in terms of fixity, so you're able to transfer moment between columns relative to their stiffness. If we look at a beam, for example, we look at the releases, nothing is released, no translational or rotational releases, and that's the same for columns. The user clearly can make those changes if needed at individual columns, or if you select more than one of the same type of element like a column or beam, we could go to modify item properties, and for columns we can go here and change the releases for a group of columns, or if beams are selected, a group of beams. So we're going to just leave everything fixed in this model, and I'll just go back and resave this. And now we're going to analyze the frame under gravity. We'll just analyze it under self-weight. So we'll go to FEM. If I did try to mesh this, it would actually tell me to use analyze structure to invoke the meshing. So we'll go to analyze structure. I'll just analyze one load combination in this case. We'll mesh this. Let's mesh this at 5-foot increments. The frame has been analyzed, and now we have many more results than what we had earlier. So I'll go back, for example, to columns. If we look at the column axial forces, this shows us an image of the axial forces. If there are shears in the column, moments, and then for beams we can look at similar types of design for beams. So again, we'll go to beam action. We're looking now at the beam moments in the frame under self-weight, and this is what's shown. So when you have a skeletal structure to interpret and see some of those results, so there are ways that we can filter. The first, kind of the highest level of filtering, is to go to single level and to navigate to the level that you would like to review. And then we can also use some options from the selection toolbar to filter viewing. So different ways to view moments in that. Ultimately, if you wanted to design these beams in this frame, we would have to go and add design cuts. So let's assume we want to design for something going on up at the roof. And let's turn off the beam moments. And we'll go back to a plan view. And I want to design this internal beam line. So I'll go ahead from strips, generate an X direction. I'll go to properties, and you can see that the X direction is indicated, so we're going to generate an X direction frame line. This is just a support line. It's a way for us to develop design cuts along the beam, and we'll go to strips, generate the design cuts, and you can see perpendicular to the support line are these cuts along the beam. If you wanted more design cuts, we can go and double click on that support line, select design section options, and here I might increase this to, let's say, 25. Once I've made that change, I need to generate the section cuts again. Now I have more data points, more design cuts along the beam. We'll go now to design the design sections, which you have to be in the single level mode in order to design the sections for the active plane. So we'll go ahead and design the sections. The program designs those sections for the combinations that were generated. In this case, these are the bending. This is the bending moment diagram for this beam line relative to the global analysis. So now I could take this and I can design it for rebar. I can go back to FEM, generate the rebar, and I have reinforcing along this line. Now, in this case, because we did not solve for strength, we're not getting any reinforcement for these beams. If you look at the beam itself, the properties of this design section under design is two-way slab. So clearly that's wrong. I need to set this to beam. and we'll go back and just redesign the design sections. And if we go back to generate reinforcement, it's telling us no rebar is required for this condition. Again, we only analyze this for service with self-weight, so we would have to analyze it with strength combinations to get the reinforcement necessary for the demand actions in the beams. Okay, we're going to go back now and we're going to look at how to analyze this frame with the definition of lateral loads on the frame as well. So I'll go back and just clear the view here for the results. I'll close result display settings, and we're now back at our multi-story frame. So the first thing we need to do is determine how we are going to apply lateral loads to this structure. And the prerequisite to that is we want to keep it as a skeletal structure. We don't want to introduce dummy slabs or slab elements that require us to mesh the structure. And so that eliminates the use of our seismic and wind load wizards in the program. If you go to loading, if we go to loading and then select the option for add load, wind or seismic load wizard, these two wizards are related to the inclusion of slabs and frames that include slabs or walls, columns, and so on. You could still have beams, but the prerequisite is there are nodes relative to shell elements, not frame elements. They would also include node and shell, or excuse me, nodes for frame and shell elements, but we have to have shells. In this case, we're constraining that and saying we're not going to have any shells. So that requires us to manually add lateral loads to this frame. And so what we're going to do is we're going to select loading, load case library, and I'm going to generate building loads in the structure. So we're going to just call this, I'll just call it X wind. I'll add that load, and I'll do one for Y wind also, just for purposes of having it in two different directions. We'll add that load as well. So now we have two building load cases. The prerequisite for having a solution that will incorporate these load cases is you must analyze the frame in global or multi-story mode. So when we add these loads, we have to run the model in multi-level mode in order to get a solution. So we'll say OK to that. I'm also going to add two combinations just so we can see the effects of those two load cases. So we'll call this wind X, and we'll call this wind Y, and I'll set this to no code check. That means the program will solve it, but it won't design it in terms of reinforcement. We'll add a factor of 1 to each of these and say OK. And now we want to add loads to the frame in order to mimic those wind forces in the X and wind forces in the Y. So I'm just going to add a lateral load to each of the nodes where the beam connects to the column. So we're going to go to a plan view, and I'll go back up to the roof level, and I'll just add some arbitrary loads to a few of these. So we'll select the option for loading, add load, point load. I'll go to the properties of the point load. This is going to be assigned to the X wind load case. This is for vertical load FC, so I'll go to loads, and we're going to add a point load here of let's do a point load of 20 kips. Okay, and I'll add that to these locations where the beams connect to the columns. And then I'll also add a line load along this edge and this edge, just to show some variance in how the loads could be assigned. So we'll add load, line load. Again, this will be assigned to wind X, and the magnitude we're going to say is 1 kip per foot. And this FZ1, we're going to change that to 0. We don't need a vertical load, just a lateral. Okay, now more loads could be added to any level in the way I just added them, and then they could be copied down, or you could go to each individual level. So we're going to run this first just with the loads applied at this upper level. And I'll make sure I go back to multi-story mode. Remember, these are assigned to a load case, which is designated as a building load case. So we have to run this in global mode. I'll go to FEM. I'm going to analyze under WindX. We'll say OK. And after we've analyzed that, we want to visually inspect the deformation of the frame relative to these loads, just to make sure that the frame is behaving, or it's deflecting the way we would expect. And I'll go to FEM analysis, view analysis results. We have the frame shown in this module called Add Viewer, and I'm going to select the X direction translation, and I'll go up to 3D, and this now becomes the displacement of the frame. So we can clearly see at the top level these beams are bending, they're in flexure and taking load out to the columns, and then these four interior columns are also displayed relative to the location of the outer columns. So clearly the loads are being applied. If we wanted to check equilibrium loads, we could go to Reports, Single Default, Tabular Reports, Analysis Data, Equilibrium Check. And this will actually show us what the applied load is in this case. So we have 40 kips times 2 at either side from the line load, so that's 80 kips plus an additional 80 kips, so there should be around 160 kips of applied load on this structure. Let's see, we have 320 for FX. This is shown right here, so I'm off just a little bit. Let's go back to the model and see what I have wrong. So this is 40, 40, 40. That's 120. Oh, that's where I'm wrong. So it's 120 plus 120. So that's 240 plus 4 times 20 plus 80. So 320. That's what I was off on. So I was only calculating but per one bay. It should have been 3 bays. So that's an equilibrium. The applied loads equal the applied or the reacting values at the base. Again, going to my result display settings now, I can look at some of the behaviors of the frame elements like columns and beams. So under I could look at axial forces. In this case, we would have tension on one end and then possibly compression on the other side. So we have a positive negative type of a couple developing in the frame. We can look at shears, moments about S. These are the primary moments due to the direction of the applied load, and so on. And we can do the same for the beams. Any set of applied loads can then be taken further into generating the design strips and the design sections for design. So if I go back to my upper roof level, let's just go back to a plan view and I'll turn off the loads. I'll regenerate my design cuts. I already have a design strip here at the middle beam line, and we're going to then design the design sections. So I have WindX. If we look at the design sections, bending moments, we now have a kind of a classical bending diagram due to lateral load in that beam line. Now this WindX is assigned to no code check, so the program isn't going to design reinforcing for this particular combination. If I change it to strength, the program will design reinforcement for strength. So I'll just go back and we'll rerun through this one more time under the loading load combinations dialog window. We're going to make WindX strength. We'll say OK, and I'll go back to global structure mode, reanalyze for that one load combination. And you can put support lines on all of the frame lines. I'm only showing it on one frame line, but you could get a comprehensive design for all of the frame lines if you added support lines for each one. And we'll go now to single level mode at the roof level, and I'm going to design the design cuts along this level. So we get back to showing those moments. Now if I go to FEM, generate rebar for envelope or for Windex, it doesn't matter in this case, we'll say OK. The program now reports the reinforcement for this beamline. And that reinforcement in plan, let's turn off the, you can see that reinforcement is shown on the screen. Let me turn that back on using the reinforcement toolbar. So we have top rebar, which is green, bottom rebar, which is red, and then the blue rebar is a special color because it's indicating that the rebar actually extends into two different elements. So here it's in one beam, and then graphically it extends into this transverse beam, so it turns blue to indicate that to the user. But this is now the reinforcement for that one load combination. If you have any questions about this video, please contact us at support@adaptsoft.com. Thank you.